There you go. So just a practical thing, and I haven't actually discussed this with Ben yet. So I get these Canvas notifications emails on a regular basis that says, this has happened since you last looked at something. And I noticed that there were a bunch of people who put comments on their submissions. I didn't go and look what they were. I just want to say that there's no guarantee that anybody will actually. Are there any guarantees? Oh, Ben will see them. There's no guarantee that I will see them. So if you want me to see something, email is the best. And after that, using Yab. If you want to send a message directly to me, I would much prefer that you emailed me rather than using the Yab message thing, because that I won't know about until I actually log in. So it could be 24 hours or something like that. And if you mail me from Canvas, then I can't reply back with any sort of attachment or anything, and it just is weird for my mailer. So a regular, good old-fashioned email, if you're trying to contact me directly, is probably the best way to do that. Benjamin is asking Benjamin if the notes from Tuesday have been uploaded.
I'll take care of that right now.
Oh, he's taking care of that right now. So well done for noticing, keeping him honest. So where can we view the Java tutorials? Oh, you know what? I'm going to message Ben about that right now. So we'll get back with an answer to that. All right, so that's taken care of. So we'll wait a response to that. How about anything else? It's still hot in here today. I'm sweaty like a little piglet. So I've opened up phase 2 and I've moved it over, and I've asked you to read chapter 5, which is a reasonably straightforward chapter to read, and I don't know that there are any major obstacles there. There are a few things that I just want to sort of draw attention to. So let's just sort of skip to chapter 5 and then come back to where we left off with common sub-expressions last time. So one of the things that we have in chapter 5 is sort of this idea that there's a correspondence. So there's a correspondence between grammar rules and parse tree nodes. And there's sort of a number of things. There's the obvious thing, which is a right hand side of a rule may often be equivalent to the children of a node, so of a parse tree node. And sometimes a left-hand side of a rule may be a node itself. And I think if we just, let me just pull up the grammar from So here's the grammar. Actually, maybe should we do the one in PDF because it's a little nicer to look at. So if I go and look at this grammar here, it is certainly not true that every left-hand side makes a parse tree node. But if I sort of start and say, right, this could be a parse tree node because it is one of these things. That makes sense. This could be a parse tree node because it's just one of these things. Now, a primitive type is just one of the good old-fashioned types that we know. And a reference type is, as we can see, a class or an array type. So there's a good chance that we would say, all right, type is probably a parse tree node by itself, but it's an abstract one because it's going to be a superclass for a primitive type and for a class or interface type, which is just called a class type, or an array type. A class type, well, that's just a name. Yes, I think so. Recording in progress, yes. So if we come down, let's go find an if statement. Here. So here are the if statements. I don't know why it's highlighting the do. But there are sort of three versions. There's a if expression statement, and then these two are basically the same. It's if expression statement, else some other statement. And if I look at what do I need in order to represent an if statement? So if we sort of just go back and think of that here. Right, so let's just take an if statement as a parse tree node. So if I have an if statement, and this sort of represents my parse tree node, what sort of children would I need underneath that? Well, what are the constituent parts of an if statement? There's the keyword if. There's one of those. Then there's an expression. And there's a statement. And then there might be an else. So how do we do it like this? And there might be a statement. And of course, this expression could be ever so complicated and have its own parse tree, and this one can be very complicated and have its own parse tree. This one can be complicated and have its own parse tree. So if I look at a parse tree or the part of a parse tree that contains an if statement, it might look something like this. Now, immediately, if you look at that, so Dennis says condition. We have there's one condition, right? That's this guy. This one is always here, and this one is always here. These guys are optional, right? So I know it's an if statement from the node that I put up here. So you could certainly argue that we don't really need the following. We don't need the terminal if bracket, that one, and that. Because why were the brackets and those things in the grammar? Well, just because we needed it to be easy to read, easy to parse, or whatever. But I don't need to recognize or need to keep the token for the keyword if I already decided this is an if statement and I'm rolling out an if statement parse tree node written in Java to contain all the other stuff. So we can really sort of say, oh, I'll get rid of this, get rid of this, get rid of that, get rid of that, and then just make a note here that says may be may be null. So now I know what my parse tree node needs. It needs an expression and two statements, and be of type if statement. So if I wanted to write that, I could go here now and say, all right, we'll say class if stat. And I'm just going to say that it extends statement. Everything extends AST because that's sort of the top node. We'll say that it extends statement, and then we'll have a generic statement abstract parse tree node so that we can group statements together in collections if we want to do that. And if I look at what the AST node looks like, let me just show you that one. And of course, this could be designed in any which way you might like to design it. But I've come up with this because I think it works reasonably well. Oops. So here's the AST node. That's the superclass of all parse tree nodes in our tree. And we can see that it contains information about lines and character beginnings, and then it has this array here called children and a variable called nChildren that just tells us how many children are in this array. It can be created in a number of different ways, based on a token, based on another AST node. You can print it out nicely, and if you ever see blah, that's because you got back to here and you shouldn't be there. So something went wrong. So we just have this basic AST node so that we can have this collection here. Now, if we look at what the if if you look at what the if statement looks like, so we can see that that's pretty much the way I started here. It extends if statement, and then it has some constructors, and then it has some accessors. And we need an accessor for each of the three things we put in. So this guy must take in an expression and a statement, or an expression and a statement and a statement, in case we have an else. And an accessor must be able to give back an expression, give back statement, or statement and statement. So if you look at what we have here, you can see we have a constructor that takes in an expression and a statement. That's the part where I don't have an else part. So here's the one that has the else part. And I'll come back to the one above in just a second. If you look at this one here, this just calls the constructor. This is an explicit constructor invocation. If you don't know what that is, please go and learn about it. It's an explicit constructor invocation of a constructor in the superclass that takes in a single AST node. And if you go look in statement, you'll see that it is there. We can look at it in just a second. Sets nChildren 3 and puts those three things here into the parse tree node. And then we provide here three accessors, one for the expression, one for the then part, and then for the else part. And you can see here it's expression, statement, and statement. The expression is the one at the 0th index, that's this guy. The then part is the first entry, that's this part, and the else part is this one here. And then it says here, note that the else part can return null, which of course is because you're not forced to have an else part in an if statement. This one here, has anybody ever seen anything like this before, and can anybody explain what's going on right there? That way I have time to drink coffee while we wait for an answer. This is one of the things that throughout this project will be people's nemesis is because they don't know what a explicit constructor invocation really is. So this is the same as that. No, it's not constructing itself, because that doesn't jive really, because you would be calling yourself, and that is a bad thing, right? It's simply invoking somebody else. So if that's what you mean, then yeah, you're right. This says whatever my superclass is, which is something of this statement type, just call a constructor in there that fits with these parameters. This means, hey, call another constructor instead of this one that fits these parameters. And of course, that's just this one. And note what happens here. I'm calling this constructor instead. So if I've instantiated an if statement with an expression and a statement, then what I get out of that is just a call to this constructor with this part here being null, right? So I might as well instead have instantiated this if statement with whatever expression I used here, whatever then part I used here, and a null for that last guy there. So it is possible to call other constructors. You can either call one of your own constructors, or you can call a constructor in the superclass. If you want to call your own constructor, it's a this call, and that's the C invocation. And, well, somebody remind me about the C invocation. We need to just talk about the body and the... We need to come back to C invocation. Somebody remind me before we leave today. Or you can call another constructor using this. Now, of course, this guy here can't call itself, so you couldn't just say this expr then part, because then you'd get an infinite call, and you can't have recursive, mutually recursive calls either. And if you have one of these, then it has to be on the first line. And if you don't put one in, one will be put in for you. You just don't know that. And that one will just say super open bracket close bracket. So that just means it calls the default constructor of the superclass in order to ensure that all your superclasses, or that all your super objects, are correctly instantiated all the way up to Java-lang object. So if you leave it out, if you leave this first line as not a super or this call, the compiler will insert for you super open bracket close bracket semicolon. So much of this stuff is covered in the video, and I don't want to spend too much time on it here because that's sort of counterproductive. But I just want to point out here that an L derivation builds a tree. So let's just say if I have something like A goes to, I don't know, A, B, let's do B, C, B goes to D, B, or epsilon, and C goes to A or C. And then let's say I have a string D, D, E, C. So if I'm going to try to derive that, actually let's do that here, then I get something like A goes to, and we know that we got to go to a B, so we're going to have to say B, C, and then we got to go D, B, C. Now we've matched that one. Should we do that again? D, D, B, C. Now we've matched this one. And one more time, D, D, E, C. Now we matched that one. And one more time, D, D, E, C. Now we've matched this one. And if I just to rearrange this ever so slightly, we'll move that down there so I have room to... Oh, Ben says he sent me the link on Labor Day. I just got to go look at my email. Yeah, we'll do that in a second. So if I have that, then look at this. I'll start with an A at the top. It's going to have children B, C. That's going to have children D, B. That'll have a child D, B. That'll be an E. And that C will be a little c. So if I note here, then these internal guys are non-terminals. And these nodes are terminals. And if I perform a depth first, left to right traversal, printing leaf nodes, what do I get? Well, let's see. D, D, E, C. D, D, E, C. Which just happens to be the string, right? So I could now say phase 2 of the project is go and design all the parse tree nodes that you need, and figure out what sort of children they need based on the grammar, etc., etc., etc. And that would be a lot of work. And I don't think anybody wants to do that, because not two people are going to get the same thing. And then Ben is going to quit because he's not going to want to mark any of the assignments. So I have given you all the parse tree nodes. Basically phase 2 is just figure out what to create where. So the thing is that in cup, if I have something like left-hand side colon equal blah 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 blah, or blah 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 blah, or blah 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 blah, semicolon, then like we did in Flex, I can put some action here. Where basically what we're going to do there is create a parse tree node. And we're going to create a parse tree node that is whatever this is supposed to be, right? Sometimes it already is that thing because of the super subclass relationship of the parse tree nodes, and we can just sort of ship it on. But whenever we want to do something with a parse tree node, we always say result equals and then something here. If you don't put that in, if you leave that out, then it's the same as saying result equals null. And very, very rarely do you want that. Now, if this guy here had been something like I don't know, if alparen, delete some of this, expr, rparen, statement. Then really what I want to do here is I want to create that parse tree node. So I want to say something like result equals new if stat, and then I got to give it, if we go back to here, then we're going to give it, well, we have to give it these guys here, right? This expression, that statement, and that statement, where this may be null, and I think in this case it probably is. Yeah. So we need to give it this part and this part. And if you think about it, this is a parsing line in the cup file. So it means by the time I get to here, all this stuff has been parsed. So I have eaten off the input something that is an expression. And before I did that, I saw the keyword if and a left parentheses, then I saw a right parentheses, and then I ate up something that is a statement. So in theory, this should be a parse tree and this should be a parse tree. And indeed, it will be if we fill in all the action. All we need is just a way to refer to them. And we can do that by just giving them names. So now in here, I can just say E, comma, S. Yep. There we go. So phase 2 is learn your parse tree nodes. And I mean this in the nicest possible way. And I cannot emphasize this enough. If you don't know your parse tree nodes like the back of your hand, all the rest of the phases will be a struggle. If you know your parse tree nodes, then they are going to be so much easier because you don't have to go looking for things because you know where to find them. So I know it's going to be a little bit of paper, but print out your parse tree nodes, one node per sheet, and then draw what would amount to this. And then note here, what are the types? And you might also want to note that this accessor is called expr. That's then part, and this is else part. And just hold on a quick second, Ben. That thing there, is there one of those out there?
Yeah.
Is there a way we can take a nice picture of that and post it on somewhere?
Be able to scan it through Punk.
I don't know if it's too big to fit in the scanner.
Well, it's a document reader.
Oh well, you can put it on the yeah, maybe we can do that. That would be great because I have a class hierarchy in color made by a lovely lady named Abby Habdas 500,000 years ago, and she's no longer here, but she came and gave me this almost laminated, beautiful thing she made in. I don't know what software she used to make it in, but it is really nice to have as well because it shows how everything fits together. And Ben has now put on his mask and walked down to the. Oh no, he's back. He needs his keys. And walk down to scan it, and we will put it up on. Will we put it on canvas? Okay, Ben can put it on canvas. At least he says so. So that one is good to have as well, and we'll put it up as a PDF or something, so you can download it and have that to work with. So once you've learned the parse tree nodes, now you got to figure out where to create what. So what right-hand side creates what particular thing? And once you've figured that out, then up at the top of your parse tree file, or parse tree, or your cup file, sorry. At the top of your cup file, you have a whole bunch of non-terminal declarations that all say AST. They now need to be adjusted to be what they really are. And none of them are AST. They all have a particular type. The reference compiler prints out a parse tree. So if in doubt, run the reference compiler on small snippets of things that you are doubtful about. Right, let me just say one thing about constructors versus methods. In a method, we have curly bracket, something, 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 curly bracket. And this is the body. And it is a sequence. So that's sort of like an array that can grow as it needs to. And in general, when we use when we have an empty sequence, we create an empty sequence so that we can reference it rather than having to use null. If I look at a constructor, it's something, 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 curly bracket, and then it's a C invocation and a sequence of statements, curly brackets. So you would think that the curly brackets would be actually, this is not a sequence, this is a block because it has curly brackets. So it's a block of a sequence of statements. This guy over here is not. The reason is that the grammar originates originally all the way back from son. So it's an original grammar, and I didn't make any changes in it, and I don't know why they did it this way. But this first line, if it's there, is a C invocation, and these second parts is a sequence of statements if they're there. Now these guys here go into a constructor body node, which doesn't appear in the parse tree, but it's simply used to transport this and this to the constructor declaration, which takes in some modifiers, some parameters, a C invocation, and a sequence of statements. And of course, we could be in a situation where we don't have one of those and we don't have one of those. So it's null empty sequence. We have one of those and we don't have one of those. We don't have one of those, but we have one of those, or we have those and those. And that all just goes into this constructor body in different ways. If you have a C invocation, it goes in. If you don't have one, you put null. If you have a sequence of statements, you put them in. If not, you put in an empty sequence. And then that constructor body that gets shipped to the previous rule for a constructor is simply there taken apart. I think it's what is it? CI and ST, I think, are the two variables inside. You can take a look. And I think that's what I want to say about this for now. And so get moving on this stuff, and we can look at questions on Tuesday, because I am sure there's going to be some questions, and that's perfectly fine. I was all by myself for office hours yesterday, and I even rushed to make it to them, and then nobody showed up. So I was, again, all by myself. But I have a feeling that that won't be a problem on Monday, maybe. Well, of course, depending on... No, it's going to be hot and gross on the weekend, so you don't want to go out anyways. Right. That was a little bit more than what I wanted to say here. Any questions so far? Or can we go back to 432? I feel like shouting boo really loudly just to wake everybody up. Are you all here still? Or is that just some robot thing that every time I ask that question, it goes, yes, 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 yes? All right, you are all most of you are here. We should have one of those, the polls you can do on WebEx, just are you alive? Yes and no, and then anybody who doesn't answer would be assumed to be dead, I suppose. Yeah, script response yet. Yes. Well, because I know for a fact that there are some people who come and sign in and then leave, because once the class is over, then whenever everybody leaves, there's always one or two hanging about, and that must be either the ones that died, fell asleep, or just left. But as I said before, you certainly don't have to be here. You don't even have to watch the videos or read the book or do anything you don't want, as long as you pass the class, because who am I to tell you what's the best way for you to learn? So we're good. Right, so we looked at left recursion last time, and I told you that I'm not going to ask you a question about eliminating indirect left recursion, but certainly direct left recursion is fair game, and it most likely will be on the question on the final. So let's try this one now, and let's start with a small example again. So let's say that I have something that looks like this: A, B, C, A, B, D, and I can ask, is that LL1? Nope, nope, nope. At least 2 out of 63, 3, 4. I'm alive and certainly not a bot, right? No, 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 no. So why is it not LL1? So if I look at the first sets, A, B, capital C, and intersect with that with the first of A, B, D, then I get A, which is not equal to the empty set, which it should be, right? Yeah, so what do we do about that? He's back. Did it succeed?
It's ever so slightly too wide for the document feed.
Well, couldn't you just put it in on the glass plate?
Not enough DPI. It's too blurry.
What?
Even at like 600, which is that thing's max apparently. Maybe? Let's see.
It didn't work. We'll find a way. Otherwise, we'll just take a picture. I don't know. The problem is if you're scanning with my scanner in my office, I don't know where it goes.
Put it on the screen, most likely.
Oh, yeah.
But like,
So do you think you scan them like 2 bits and then just glue them together or something? As in, like if you copy it, if you cut it in half.
well, yeah, but it's too wide this way.
Yeah, but if you cut it in half.
Like that.
No, the other way.
Like that.
Yeah.
Well, I still think it's going to be too wide.
Well, can't you just cut some of the whiteness off?
That's what I was thinking.
Yeah. Now we just got to figure out where the scissors are.
Well, and then it's also like I don't know if the DPI of the document feeder is going to be good either.
Who knows? Well, we'll sort something out. Oh, you can use the scanning app for your phone. Yes, that's true.
I don't want to do that.
I have that scanning app.
I'm not. You can do it.
Okay, well, I'll give it a go after class. Right. So, back to this. So, what does Daniel say? He says A goes to A, B, B, and then B goes to C, D. Right. So, the suggestion says A goes to A, B. B. You know what? If you don't mind, I'm going to call it A prime. A prime goes to C or D. So is that a solution always? Not always. So when could this go wrong? So if C and D share anything in the first set, right? So if first of C intersected with first of D is empty, then we're golden. And if it is not empty, then we're not so good. Now, if I assume here that C and D are non-terminals, then the best we can do is this red rewriting and then go and look at C and D and see if we can do something about them. So the way to eliminate common sub-expressions is simply to find the longest prefix that things have in common that exhibit this problem because of common prefixes, and then just lift them out. So in general, just like we did with the with the left recursion, if I have A goes to A1 dot 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 AN, where AI is a mixed string, so a mixture of terminals and non-terminals, then we can say something like let alpha be the longest substring such that AI is equal to alpha AI prime. So that's just a fancy way of saying that in this case here alpha is AB because they all have AB in common. So this is just, so alpha is just the common sub-expression. Then it's pretty clear what we do. Then we can just rewrite as A goes to alpha A prime goes to A1 prime dot 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 AN prime. Now, if not all of the A's up here have an alpha, then it's not a problem. We're just gonna leave them as choices here. So in other words, if AI is equal to alpha AI prime, and A goes to A1, A2 dot 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 AN, B1 dot 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 BN. Should we do M there? And no BI is equal to alpha BI prime. So none of these B's start with alpha, but alpha is the biggest common sub-expression between all of them. Then we can simply say A goes to alpha A prime or B1 dot 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 BM, and A prime is A1 prime dot 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 AN prime. Okay, so super simple, nothing to worry about there. It only gets a little complicated when we start mixing the two things together. Right, onwards and upwards. 433, which is grammar ambiguities. And let's, as usual, start with a small example. So what do you think? Anything you can tell me about this grammar? And anything you'd like to do to it? There's left recursion, yeah? Or maybe one thing I should have noted here when we talked about this, this alpha here is I think it's terminals only, isn't it? No, and non-terminals. So it could be both. So it has left recursion. Be careful, Daniel. Very, very careful. Because you say the first set union is E. That is not true. What's wrong with it? Now we're going to pick on you because you participated. E is not a terminal, right? So first sets always have terminals in. So left recursion means it could still be LL1. No, I think we came to the conclusion last time that left recursion always breaks the LL1ness, because at some point you're going to have to end up taking this guy here, right? Which means that you're always going to get an ID here and an ID here. So regardless of what you do, you're always going to end up with these two having something in common, these two having something in common, and these two having something in common. That's okay, Daniel. Now you won't forget it. So yeah, you're going to say, you say that these guys have ID in common, these have ID in common, and these have ID in common. Yeah, so there's that. Right, so so we can say intersecting first sets fails. Ben is back. Let's see, is he looking happy? He really should be a system administrator. Yes, yeah. Yeah, he has the homogeneous gene for that. Right, so what can we do about this? There's something else I want to just point out, if you don't mind. So let's see. I'm going to try to derive E plus E plus E. So I'm going to do it in purple here. And I'm going to do a leftmost derivation because we like to do those. And then I get E plus E. Right, leftmost derivation, so we've got to develop this E guy. So I'll go ID plus E. Oh, can I just move that up a little bit? And then we'll do ID plus E plus E. ID plus ID plus E. And if you catch me cheating anything here, you'll just let me know, and we'll go back and look at it. All right. What does the parse tree look like for that? E there, that's this E, and then we have those as a children. It's a good thing we talked about that. And here I'm just going to add it all in. So we get that. This left I becomes an ID. This becomes an E plus an E. This is an ID, and that is an ID. Right. Now let me try another one. I'll do leftmost derivation again, just so we don't screw anything up. Now that E becomes E plus E, and then we already had an E. And then we can just turn all those into IDs. And then we get a parse tree that looks like this. There you go. Which one is the correct one? So this would have maybe been better if we'd done it with minuses. Both and neither are the same. Both, well, no, one is correct and one is not correct, because what happens if I said so let me just over here say so if I say ID minus ID minus ID, is that E minus E ID minus oops E ID ID, or is it E ID minus E minus E ID? So in other words, if I have 5 minus 2 minus 9, is that, what is that equal to? Is it 5 minus 2 minus 9, or is it 5 minus 2 minus 9? That one here is 3 minus 9 is 6. This one is negative 7 from 5 is negative 2. Left one, Louis says. So we always bracket left to right if the brackets aren't there, right? So it's 5 minus. So this reminds me of those stupid things on Facebook. Ben wouldn't know because he doesn't know what Facebook is, where 95% of the population cannot answer this question, and it's one of those simple rules where the first thing you have to do is multiply the things that need multiplying, and then you just add it all up. And 95% of people really can't do it, right? And they can argue about it till the cows come home, and then somebody says, "I'm a math teacher. The answer is so and so." To which point they still argue about the fact that the math teacher is wrong because they certainly couldn't know what they're doing, right? Well, the problem is those math questions are not ambiguous, right? Because the rules say exactly what to do. Do your multiplication and division first, and then do your minus. So there are precedence rules, right? So what happens first? Well, multiplication and division happens before addition and subtraction, and exponentiation happens before any of that, and brackets take precedence over most things. So there are certain rules for how to do that. Now, how do I get that into a grammar is the question. and we're going to have to come back to that. But let's try to see if we can solve the ambiguity question with just the plus or minus operators. So actually, we can solve it just with plus, right? Because plus and minus have the same precedence, so it's not a big deal. So just to make it easier. Now, we want this guy here, so I'm just going to make a copy of it. And put it there, and then say the correct one. Now, what went wrong here? What went wrong here, of course, was that in this derivation, this guy became ID. So here, this one just became that one. And over here, this one became all of that. So that one became that, whereas over here, that became that. And of course, that's possible because of both of them being E's. Now, if I look at the, which one was it that we liked? We liked the green derivation, right? So that means that the left recursion on E becoming E plus E is correct. But I don't want the other one to be an E. So couldn't I just say, hey, you can be all the other stuff except for E? So if I have E goes to E plus E or ID, then this one is okay. This one should only be an ID. Well, I think we can solve that fairly easily by saying, right, we'll allow this recursion here, and then we're going to say plus F, and then F becomes ID. Now, of course, we have the problem that we're going to recurse forever because E can't become anything, but the right-hand side, so we'll say, right, we'll skip directly to what where we had ID before, which is F. So now we get this. So now let's try again. Right, so if I say E goes to E plus F goes to E plus F plus F goes to F plus F plus F goes to ID plus ID plus ID. And what does that parse tree look like? It looks like this. And I think that one is correct, isn't it? Isn't that the one we wanted? The one we wanted is the one that sort of hangs off to the left. If I have a whole string of things that are just being added or subtracted, right? So this one sort of hangs off to the left as well. Right. So that's fine. How'd you like this grammar then? I think I'm sort of back to where we started when I asked you about this. Although I feel I've solved one problem, which is the ambiguity of the operators there, or of the parse tree. Sorry. But it is still left recursive. All right, fine. So let's grab that copy, plunk it down here. There we go, and let's just remove the left recursion. Well, that's easy enough, right? Because we remember that we said, right, that's the recursive case, and this is the non-recursive case. So this is E, this is alpha, and this is beta. So should we just put some names on here? So this is A, this is A, this is alpha, and this is beta. And we know that A goes to A alpha or beta becomes A goes to beta, A prime goes to alpha, A prime, or epsilon. Good, then we can just do that. So we get E goes to, and we need beta, which is F, and then we need E prime, and E prime is plus F E prime, or epsilon. So there we go. Now, if I were to throw in minus, and I said, all right, E goes to E plus F, or E minus F, or F, and F goes to ID. Sometimes, yeah, we'll just go like that. Then that's fine, right? Because they have the same precedence and everything is hunky-dory, so we just rewrite E goes to F E prime goes to minus F, sorry, plus F E prime minus F E prime, or epsilon. And F, oh, we forgot up here, F goes to ID, and F goes to ID. And Bob's your uncle. Right, so we solved the ambiguity stuff, we've solved the left recursion problem. Now we have to solve the precedence problem. Right. So let's see, if I have A plus B multiplied by C, and I have A multiplied by B plus C, what is the parse tree supposed to look like? Well, let's see, plus A multiply B C plus C multiply A B. So what do we see from that exercise? We see that this is lower than that. This is lower than that. So in general, higher precedence means lower in the tree. Now, why does it mean lower in the tree? Can anybody give a reasonable explanation as to why that is? No, LL is not bottom up. LL is definitely top down, because we replace left-hand sides by right-hand sides, and therefore you build the parse tree from the top and you replace the non-terminals as you go down. Michael says, because the lower expressions are solved first and return their answers to the above expressions. Yes, I think you might be right. I don't like the way you phrased it, because there's no expressions that are solved. This basically just has to do with getting lingo correctly. And I know for a fact that there are some of the professors previously that have let it slide, but I am not one to do that. So lower expressions are solved first. If you're looking at the expression that is represented by the parse tree, in order to evaluate the expressions, the lower parts of the parse tree have to be evaluated first. That is correct. So because multiplication binds with a higher precedence than plus or minus, we have to get something like that, right? Because B and C have to be tied together in a lower subparse tree so that they can be evaluated if I'm trying to evaluate them. And Michael says, because nodes resolve their children first. I'm not entirely sure what that means. And Dennis says, because those get their terminals first. I think I know what you mean. I don't like the the phrasing of it. I think that the answer there that Dennis gives is it's sort of a little circular because it gets its terminals first because I made them like this. Not answering so much as to why I have to make it like this. Basically, if I want to evaluate this, just think about it. It's really sort of straightforward if you think about it. I have virtual brackets around that and that, which means that B and C must be tied together with the multiplication symbol here, just like they have to be tied together with the multiplication symbol here. And then the plus happens afterwards. The very confusing thing about this is that the lower precedence operators appear higher in the tree, whereas the higher precedence operators appear lower in the tree. Okay, so what do we do about that then? So if I have E goes to E plus E or E multiplied by E or ID, well, then we can certainly do something where we say E goes to E plus F or E multiplied by F or ID, and F goes to, oh sorry, that was supposed to be an F, ID. But that doesn't solve the problem, right? We need to do something like this. So we got to figure out a way to get the multiplication to be a stronger operator. So how about we do this instead? What if I say, right, if I want to do a plus, then I can certainly do so. And if I don't want a plus, then I'll just take the T. So I can plus things together using the plus. It is the lowest precedence, so it's sort of the one that ties everything together. Now, what is T going to be then? Well, T is going to be the stuff with higher precedence. Okay, well, then that could just be the multiplication part. But if I don't want to do multiplication, I got to be able to escape that as well. So we do something like that. So now every term that I'm adding together can either be an identifier or it can be something I multiply. Right, so that seems like a reasonable approach, but now we got this problem. But we know how to solve that. This is not a problem that we cannot handle easily because we can do this with our eyes closed. E goes to T E prime or T. E prime goes to plus T E prime or epsilon. T goes to F T prime or just F. T prime goes to multiply F T prime or epsilon, or F goes to ID. So there we go. So now we have the tools to massage a context-free grammar into a form that is more likely to be LL1. So now, unless there are any questions, I just want to give you the beginning of recursive descent parsing. Right. So let's start with an example that isn't written as an example. Let's say that I have a rule that looks like this. And let's say that I say for all I and j, first of alpha I intersected with first of alpha j is empty for first, and I of course is not equal to j. So I got that. Is it true that the following statement, well, is the following statement true? Let me write it down. For all little a in sigma, so that's all terminals, we can always pick the correct alpha I when parsing an A, or produce an error. Is this true? Question mark. Wow, we're down to 55 people. Half the class. So true or false? So Louis says yes, because there's no first of any alpha that intersects with any other first of alpha. That is correct, right? So if I promise you that this is the case, then we basically have two options. We have two options. We have option one, which is there exists some I such that A is in the first of alpha I, or no matter which I pick, A is not in the first of any of them. And if that is the case, so that if that bottom one is the case, then none of the alphas would have been able to produce a string that starts with the look ahead on the input. So we can produce an error. What should I do in the first case? Well, there is exactly one, because we know there are not two, because if there were two, some of these sets would intersect non-empty. And that one we found is alpha I, so just parse alpha I in some way. So with that knowledge, if this, if this is true, and I'm gonna put a disclaimer on this. Let's not worry too much about epsilons, because epsilons are somewhat painful to deal with. Well, the thing is, I could never, I can never see an epsilon on the input, or I can always see an epsilon on the input, because an epsilon is nothing, and well, you could always see I see nothing on the input. That's right there in front of something, right? So that just becomes a little bit iffy, doesn't it? But if we're just looking at these two options, it seems that if I have a good old-fashioned terminal, and that terminal exists in just one of the right-hand sides, well, it must have come from there, if the string is parsable. And if it doesn't fit into any of the right-hand sides, well, then we can produce an error. So could I not write something that looks like this? So how do you spell therefore? I've forgotten that all of a sudden. T-H-E-R-E-F-O-R-E. Therefore, we should be able to write some actual code that looks like this. Void, what do we call it? We called it A. Parse A. All right, and it's going to say something like, if the look ahead is in the first of alpha 1, then parse alpha 1, whatever that means. Else, if the look ahead is in the first of alpha 2, then parse alpha 2. Otherwise, else if the look ahead is in the first of alpha n, then parse alpha n. Else, so if it failed to be in the first set of any of the right hand sides, then we couldn't have produced it. Else error. So something like that. And now we're going to leave, but just think about the following thing. If alpha I is chosen, so let's just say for fun that we're here. If alpha I is a mixed string that starts exactly with the terminal that is on the look, that's the look ahead, then what do I do? Well, then I can eat that look ahead off of the input and move on. So every time I get to a terminal, that has to match what's on the input. How do I handle non-terminals? Well, I just call the appropriate parse function, because I can write a function like this for every single one of them. And we'll look at that next time, and then we'll see what happens when epsilons start to sneak in, because epsilons are a pain. And then once we've sort of come to terms with that, we will look at follow sets to knock out that problem, and then we'll get on to table-driven predictive parsing, which is just a nice way of tabularizing this recursive descent stuff and making it a little better. Any questions that we need to resolve now? If not, for the people who sat through it all, have a good weekend, and I'll see you on Monday for the people who come to office hours. And if you don't come to office hours, then I'll see you on Tuesday. And remember to stay in. It's hot and gross outside, so later.